In this video, we're going to talk about buffer solutions. A buffer solution is composed of a weak acid and the conjugate weak base. So let me give you some examples of that. HF, hydrofluoric acid, that's a weak acid. The conjugate base of HF is fluoride. All you got to do is remove a hydrogen. So we're going to pair up fluoride with sodium. So here we have the weak acid and the conjugate weak base. Together, these two components form a buffer solution. Another example will be acetic acid, which is a weak acid. The conjugate weak base of acetic acid is acetate, C2H3O2-. And we'll pair it up with a sodium ion. So sodium acetate will be the weak base. These two combine, they create a buffer solution. Or let's say if we have hydrocyanic acid, HCN, with its conjugate weak base, sodium cyanide, this too will create a buffer solution. So a buffer solution is composed of a weak acid and the conjugate weak base. The purpose of a buffer solution is to maintain a constant pH level throughout the solution. It resists changes in its pH. Now, it has the ability to do that because it contains both a weak acid and a weak base. So let's say if we have a solution of HF and sodium fluoride. So we have a buffer solution. If we were to add acid to this solution, let's say hydrochloric acid, instead of HCl, let's use H3O+. So if we were to add acid, or anything that would increase the H2O+ concentration, the acid is going to react with the weak base component of the buffer solution. So it's going to react with fluoride. And so we're going to get HF and water. If fluoride wasn't there, the pH would decrease dramatically. When you have a high level of H3O+ or hydronium ions in a solution, the pH will be very low. And that's what acids do. Whenever you add an acid to a solution, it brings down the pH. But because fluoride reacts with the incoming hydronium ions, you're not going to have a significant drop in pH because it will quickly consume these ions in the solution, creating HF and water. Now let's look at the other situation. Let's say if we add a strong base like sodium hydroxide. If we immediately increase the hydroxide ion concentration, the pOH of the solution is going to go up. I take that back. The pOH is going to go down rather. The pH is going to go up. These two are related to each other. Remember, the pH is 14 minus the pOH of the solution. So when the pOH goes down, the pH goes up. Now, once you add hydroxide, it's going to react with the weak acid component of the buffer. So it's going to react with HF. HF is going to quickly consume the hydroxide ions, creating fluoride and water. And so because HF quickly reacts with hydroxide, we're not going to see a sharp decrease in the pOH of the solution, nor will we see a sharp increase in the pH. The pH will increase slightly, but not by that much, because these are being reacted with HF. And so that's how a buffer solution can maintain a relatively constant pH level in the solution. It's by having the ability to react with any incoming acid or any incoming base that is added to the solution. Now let's talk about how we can calculate the pH of a buffer solution. So let's say we have a solution with hydrofluoric acid and water. And this solution also contains fluoride. So in this reaction, we have the weak acid and the conjugate weak base. So we have a buffer solution. Everything is in the aqueous phase except water. If we were to write the equation that is associated with Ka, the acid dissociation constant, this will be equal to the concentration of the products divided by the concentration of the reactants. So water is not included because it's in the liquid phase. Now what we're going to do is we're going to take the negative log of both sides of the equation. So we're going to have negative log of Ka, and that's going to be equal to negative log of the right side of the equation. So we have F minus times H3O plus divided by HF. Now, a property of logs allows us to split one log into two separate logs. So for instance, let's say if we have log AB, we can write this as log A plus log B. So let's say fluoride is A, H3O plus is B, and HF is C. We could also do this. If we have log AB over C, we can split B from A and C. So we can say this is log A over C plus log B. We don't have to separate A from C. We can keep them together or we can separate them. Right now, I want to take out H3O plus out of this expression. So B would correspond to H3O plus. I'm going to keep A and C the way it is. So I'm going to use this property of the log expression. So this is going to be negative log Ka, and that's going to equal, so we need to distribute the negative sign, so keep that in mind, negative log, we're going to have A over C. Actually, let's write log B first. So this is going to be negative log H3O plus, and then we're going to have log A over C, but with a negative sign, because this has to be distributed. And then minus log, and then it's going to be the base over the acid. So fluoride is the base, HF is the acid. Now let's go ahead and delete some of the stuff that we have here to make some extra space. Now some formulas that you need to be familiar with are these two. You know that the pH is equal to the negative log of H3O plus. You've seen that many times before at this point. Also, you know that the pKa is negative log Ka. So we can replace this with the pKa. We can replace this with pH. So we have pKa is equal to the pH minus the log of the base. In this case, the base is F minus divided by the acid, HF. Now you could put this in parentheses to indicate concentration, but since you have a ratio, it could be in moles as well. Because moles and molarity, they have the same ratio, given the same volume of the solution. Now what we're going to do is we're going to isolate pH. So I'm going to take this term and move it to the other side. It's negative on the right side, but it's going to be positive on the left side. So the pKa plus log of the base over the acid. Now I'm going to replace this with a more generic form of the base, which is typically A minus, and the generic form of an acid would be HA. On the right side, we still have pH. Now I'm going to reverse these two equations. I'm going to put pH on the other side, and I'm going to put this on the other side. So if we simply reverse these two equations, or just reverse the equation rather, by switching both sides, we're going to get the Henderson-Hasselbalch equation. So this equation helps us to calculate the pH of a buffer solution. So the pH is equal to the pKa of the acid plus log base over acid. A minus is the weak base component of the acid. HA is the weak acid. So that's how you can calculate the pH of a buffer solution. It's by using the Henderson-Hasselbalch equation. So the pH is dependent on the ratio of the conjugate base to the conjugate acid. Now there are some things that we can discern from this equation. What can we say regarding the pH of a buffer solution when the concentration of the weak acid is equal to the concentration of the conjugate base? If HA equals A minus, what can we say about the pH? If this is 10 and that is 10, 10 over 10 is 1. If this is 0.5, that's 0.5. 0.5 over 0.5 is 1. So whenever these are the same in a 1-to-1 ratio, you get log of 1. Log of 1 is 0. So this disappears. Thus we have the pH is equal to the pKa. So whenever you have a buffer with an equal amount of weak acid and weak base, the pH will be equal to the pKa. So let's say if you want to create a buffer solution with, or that's centered at a pH of 4.5. If you want to create a buffer solution that's centered at that pH, well, you want to find an acid with a pKa that is very close to 4.5. Likewise, if you want to create a buffer solution with a pH that's centered around 6.0, you want to look for an acid that has a pKa of a value that is close to 6.0, close as possible. The closer, the better. So that's how you can create a buffer solution that's centered at a given pH. It's by choosing the appropriate acid with a pKa that is very close to the pH. Now let's talk about the ratio of base to acid and acid to base. Log 10 is 1. Let's think about what that means. So let's say if A minus is 10 times the value of HA. Let's say this is 1m and HA is 0.1. 1 divided by 0.1 is 10. Log 10 is 1. And let's say the pKa is 4. What's the pH? The pH is going to be 1 unit higher. Whenever the ratio between acid to base or base to acid, when it differs, whenever you have a 1 to 10 ratio, the pH is going to be 1 unit away from the pKa. If you have more of the acid, it's going to be 1 unit lower than the pKa. If you have more of the base, it's 1 unit higher. Log of 100 is 2. 100 is 10 squared. A property of logs allows you to move the exponent to the front. So log of 10 squared is the same as 2 log 10. And log 10 is 1, so you get 2 times 1, which is 2. So log of 100 is 2. Therefore, if the ratio between base to acid or acid to base is 1 to 100, the pH will be 2 units away from the pKa. Log of 1,000, which is log 10 to the third, that's equal to 3. So if the ratio of acid to base or base to acid is 1,000, the pH will be 3 units away from the pKa. So let's say the pKa of a certain acid, we're going to say it's 4. Actually, let's make it 6. And let's say the numbers on this line represents the pH of the solution. When the pH is 6, we're going to have equal amounts of base and acid. So 50% will be base, and 50% will be the weak acid HA. Under those conditions, the pH will equal the pKa. So we can describe that as a percentage, or we could say, we have 1 molar of the conjugate base and a 1 molar solution of the conjugate acid. At a pH of 7, let's keep the amount of base the same. Let's say it's 1 molar. The amount of acid will be 10 times less. It'll be 0.1 mHa. So as you can see, here we have more base than acid, so the pH is going to be higher than the pKa. What will be the situation at a pH of 8? So if we have the same amount of base, the amount of acid will be 10 times less. It's going to be 0.01 m. So anytime the pH is, anytime you have more base than acid, the pH will be greater than the pKa. So on the right side, where A minus, that is the weak base component of the buffer, if it's greater than HA, or will be greater than HA, under those conditions, the pH will be greater than the pKa. Now what if we had 1 m HA and 0.1 m A minus? What's the pH? So here we have more of the acid than the base, so the pH is going to be less than the pKa. And the ratio is 1 to 10, so we're going to be 1 unit away from the pKa. Therefore the pH here will be, it's going to be 5. Likewise, let's say if we have 0.01 m A minus and 1 m HA, the ratio between acid to base, or base to acid, is like 1 to 100. So log 100 is 2. We're going to be 2 units away from the pKa. Or let's say if we have 0.001 of the base and a 1 molar solution of the acid, the ratio is 1 to 1,000. 1 divided by 0.001 is 1,000. So we're going to be 3 units away from the pKa. So that's how you can determine the pH of a buffer solution conceptually, by looking at the ratio between base to acid or acid to base. And remember, if you have more of the acid than the conjugate base, the pH is going to be less than the pKa. And if you have equal amounts of acid and base, the pH will be equal to the pKa whenever you have a buffer solution. Now let's go ahead and work on some practice problems. Number 1, what is the pH of a solution consisting of 0.75 molar acetic acid and 0.5 molar sodium acetate? And we're given the acid dissociation constant of acetic acid is 1.8 times 10 to the minus 5. Feel free to pause the video if you want to work on this problem. So what we're going to do is we're going to use the Henderson-Hasselbalch equation, because we have a weak acid and we have the conjugate weak base, which means we have a buffer solution. The pH is going to equal the pKa of the weak acid plus log of the base. The base we can write as A minus, or you could simply put B for the base and then A for the acid, or you can write HA if you want. I like to write B over A, base over acid. Now the first thing we need to do is calculate the pKa of the weak acid, and that's negative log of the Ka. So we have the Ka value, which is 1.8 times 10 to the negative 5. So the pKa of acetic acid is 4.7447. So now let's plug it into this formula. So that we have the pKa, it's this number, and then plus log the base. This is the base component of the buffer, so the concentration is 0.5 molar, and the concentration of the weak acid component is 0.75 molar. The unit to molarity will cancel because we're dealing with a ratio here. So let's go ahead and plug this in. 4.7447 plus log 0.5 divided by 0.75. This is, you can round it to 4.57. So that's the answer for this problem. So that's how we can calculate the pH of a buffer solution. Now there's one more thing I want to mention regarding this problem. Notice that we have more of the acid than the base. Because we have more of the acid than the base, the pH is going to be less than the pKa, as we discussed earlier in this video. Here we can see the pH is 4.57, the pKa is 4.74. So the pH is less than the pKa because we have more of the acid component than the base component of the buffer. Number 2, what is the pH of a solution containing 0.15 moles of ammonium chloride and 1.5 moles of ammonia? And we're given the Kb, the base dissociation constant of NH3. So what should we do here? Well, once again, we have a buffer solution. We have the weak acid and we have the weak base, the conjugate weak base. Now in this case, notice that we have more of the base than the acid. We have more of ammonia than ammonium chloride. So what can we say about the pH and the pKa? The pH is going to be greater than the pKa because we have more of the base than the acid. Let's go ahead and calculate the pKa. We're given the Kb, so we need to calculate the pKb first. pKb is negative log of Kb. So this is going to be negative log of 1.8 times 10 to the minus 5. And we've seen that value. So this is 4.74473. Now, the pKa plus the pKb, these two, they add up to 14. So to calculate the pKa, it's going to be 14 minus the pKb. So 14 minus 4.74473. That gives us a pKa value of 9.25527. So since we have more base than acid, we know that the answer, the pH of the solution, has to be greater than the pKa. It has to be greater than 9.25527. Let's round that to 9.255. So let's go ahead and calculate the pH of this solution. But before we do that, notice that the ratio of base to acid is 10 to 1. 1.5 divided by 0.15 is 10. Whenever the ratio is 10 to 1 or 1 to 10, we know the pH will differ from the pKa by 1 unit. And since we have more base than acid, 1 unit higher than this number is going to be 10.255. Therefore, conceptually, we know that the pH of this solution should be this value, And we're going to confirm it by calculation. So we should get 10.255. So let's write the buffer equation. pH is equal to pKa plus log base over acid. The pKa is 9.255, and then we can add the 27 as well to get a more accurate result, and then plus log. Now, as was mentioned before, this could be in units of molarity or it could be in moles. Both units will cancel. So we're going to plug in the moles. We have 1.5 moles over 0.15 moles. So we can cross out these two units. Now let's plug this into our calculator. 9.25527 plus log 1.5 over 0.15. This will give you 10.25527. So that's the pH of the solution. So we could see why it's 1 unit higher. It's because the ratio of base to acid is 10 to 1. Number 3, calculate the pH of a solution containing 15 grams of hydrofluoric acid and 21 grams of sodium fluoride in 750 milliliters of solution. So once again, we have a buffer solution, but this time we're given the grams of the acid and the base. Before we had the molarity, and during the second problem we had the moles. For this one, all we need to do is convert grams to moles, and then we could use the buffer equation. So let's do that first. So we have 15 grams of HF. To convert it to moles, we need to know the molar mass. The molar mass of hydrogen is approximately 1. For fluorine, it's 19. So this is approximately 20 grams per mole. So 1 mole of HF has a mass of approximately 20 grams. So we can cross out the unit, grams of HF. It's going to be 15 divided by 20, which is 0.75. So that's how much moles of acid we have in this solution. Now let's start with 21 grams of the base, NaF. Now let's convert that to moles. Sodium has an atomic mass of approximately 23, and for fluorine is 19. 23 plus 19 is 42. So 1 mole of NaF has a mass of approximately 42 grams. 21 divided by 42 is 0.5. So we get 0.5 moles of sodium fluoride. So now that we have the moles of the acid and the base, we can now calculate the pH. But first, let's calculate the pKa. The pKa, which is negative log of Ka, and Ka is that number. So we have the negative log of 7.2 times 10 to the negative 4. And so that's going to be 3.1427. So now that we have that, let's use the Henderson-Hasselbalch equation to get the pH of the solution. So the pKa is 3.1427 plus log of the base. The base is, by the way, will the pH be greater than or less than the pKa? So notice that we have more of the acid than the base. So because we have more of the acid than the base, the pH is going to be less than the pKa. So the pH should be less than 3.1427. The solution is acidic. So now let's go ahead and continue with this equation. So the base is 0.5 moles. The acid is 0.75 moles. So let's plug this in. 3.1427 plus log 0.5 over 0.75. This is going to be approximately 2.97, which is less than 3.14. So that's the pH of the solution. So anytime you have more of the acid component than the base component, the pH will be less than the pKa. Number 4. What is the pKa of an unknown weak acid if the pH of the solution was measured to be 5.62 when HA is 0.45 and A minus is 0.85? So we want to calculate the pKa if we know the pH and the concentration of the weak acid and the conjugate weak base. So let's start with the buffer equation. pH is equal to pKa plus log base over acid. Now what we need to do is we need to isolate pKa. So I'm going to take this term, move it to the other side. So it's positive on the right side, it's going to be negative on the left side. Now I'm going to switch the left side of the equation with the right side of the equation. So we could say that the pKa of the unknown weak acid is going to be the pH of the solution minus log of the base over the acid. So this is how we can calculate the pKa of an unknown weak acid. All we need to know is the pH of the solution and how much of the acid and base that we've dissolved in the solution. So the pH is 5.62. The base is the concentration of A minus, so that's 0.85. The acid is the concentration of HA, so that's 0.45. So this is going to be 5.34. So this is the pKa of the unknown acid. Now let's see if our answer makes sense. So whenever the base is greater in concentration or in quantity than the acid, we know that the pH is going to be greater than the pKa. Is that the situation here? Well, the pH is 5.62. The pKa is 5.34. So we can clearly see that the pH is greater than the pKa, so this answer makes sense.